Folks, welcome to this video, and if you're looking at your screen right now, you're probably wondering what on earth. This is Paula Deen. For those of you who don't know Paula Deen, she used to be having a cooking show on the Food Network channel, but she was pulled off. She's no longer on there, and she's riding a stick of butter. Why? Because she was known for butter. Butter, y'all! Everything that she would fix would have butter in it. So you're probably wondering, how on earth is this really a factor in organic chemistry? Folks, butter is just pure organic chemistry through and through. The structure of butter is all organic chemistry based. Well, the reason that I'm telling you and showing you Paula Deen riding a stick of butter is because we are getting ready to talk about this process that we call hydrogenation. And if you go to the grocery store, and if you go to the dairy section, you're going to see butter and you're going to see margarine. If I send someone to the grocery store and tell them to pick me up a stick of butter and they come back with country crock, I'm going to get mad. Yeah, folks, there's a difference. Don't know if you ever knew a difference or not. For those of you that don't cook, you probably never knew that there's such a thing. Butter is different than margarine. Butter and margarine are related, though, and they're related through this process of hydrogenation. Yeah, that's right. It's taking part in the food industry. I mean, this is the major thing where hydrogenation is going to be, because on margarine, what you're going to see is a slogan that says partially hydrogenated vegetable oil. So what this means, I can't believe it's not butter or country crock or any of those other brands that have margarine. There's a group of people that have taken vegetable oil that you can buy in the grocery store, that's a liquid, and they hydrogenate that vegetable oil to make it a semi-solid. Now, it's called partially because they don't completely hydrogenate them, because if they completely hydrogenate it, then it's going to turn into a solid. And you probably don't want to work with solids, having to chip away at it with a knife or whatever you decide to use to try to spread it onto your toast. You want something that's a little bit spreadable. Not too much effort has to go in it. It's all about convenience. Well, partially hydrogenated vegetable oil, they're taking vegetable oil, they are partially hydrogenating it, and they are turning it into a semi-solid, and that semi-solid they are calling margarine. Well, they also add some food coloring and stuff into it as well, because if you buy butter, you're going to see a yellowish color. So would you want to use margarine if it wasn't a yellowish color that looked like butter? I think that you would feel really uncomfortable with that. So they start mixing in additives into this whole mix, and they pour it into a tub, or they mold it into a stick, and they put it into a case, and they sell it to you at maybe half cost. Because butter's the real stuff. That's a little bit more expensive. And margarine is almost laboratory made, in a way, if you want to think of it that way. So, folks, we've got to talk about what hydrogenation means. You know, what is it? What's the reaction steps? Well, we're getting ready to learn. It's all about organic chemistry here. Organic chemistry turns our vegetable oil into margarine. That is a butter substitute. So, let's talk about hydrogenation. Hydrogenation. What do you see here in the very beginning? The word hydrogen. Hydrogen is H2. That's what we use. Go figure. I told you this is not rocket science. They try to make it at least very straightforward. You just got to look at your words. And here is a word that we know. Hydrogenation. Hydrogen. Hydrogen is H2. So this reaction requires H2. Hydrogen gas. Very explosive, by the way. Well, we also have to incorporate something else other than hydrogen, and we typically need a catalyst in order for this process to work. And this catalyst is normally some type of metal, some type of solid stationary phase. And there's a couple of choices for metals that are out there, all of them kind of expensive, but there's a couple of choices. The first one is platinum. PT, platinum. Could you imagine going to a jewelry store and buying a platinum ring and then me telling you, oh, we're just going to use a piece of platinum in the lab and do some hydrogenation labs? Please give me a break. The other one is palladium. PD or nickel. Ni. And all of this really supplies a surface. One of these supplies a surface for this reaction to take place on. That's the purpose of the catalyst. Okay? Hydrogen, this is a gas. And we are expecting to react this with alkenes. Alkenes are liquids. So the problem in the very beginning when this was discovered was, how on earth do we make sure that this gas, that particles hate each other, they don't get along, they're haters, and they just try to fill up as much space as possible? How do we ensure that that gas actually comes in contact with this liquid and make sure that we can perform a reaction with that liquid? So what they discovered is that this process happens a little bit easier if they take a piece of metal, one of these three, and they place hydrogen onto that metal, almost like a solid surface. And this anchors the hydrogen in place. That's the way I want you to think about this. So the hydrogen becomes stationary. And then what we can do is we can take these double bonded molecules, these alkenes, and we can just flow them across the surface of this piece of metal. And as they flow across the surface, they're scraping the hydrogens, and that is what's causing the reaction. This is the purpose of the catalyst, folks. That catalyst, the palladium, the nickel, the platinum, it is not getting used up. It's not generating product. It is only there to lower the energy of activation. And it's there to allow this process to happen a little bit easier. Now, the platinum, the palladium, these different types of metals, I just told you just a surface. And you might be thinking of a plate, a metal plate. That's not really what happens here, okay? This is ground up. I want you to think of powders. The reason is that it increases the surface area of the metal. And then we coat those particles with the hydrogen that we want reacting against the alkene. That's the purpose of that. So think of a ground up, maybe coffee grounds type of metal. That metal has been modified, and that metal has been modified with hydrogen. In the mix of this, though, we also typically will throw in a little bit of carbon. Carbon is just basically graphite. That's all that is, or charcoal. And they mix both of these up. It helps improve the stability of it. It helps increase the mass of what we need to use. It doesn't interfere with anything. Carbon's pretty stable just like on its own. And this is organic anyway, so carbon kind of is a natural match here. So with these reactions, you will see PT/C, and that is what that means. Platinum mixed with some carbon. Palladium mixed with some carbon. Nickel mixed with some carbon. Sometimes they're just okay with just normal nickel. It doesn't need carbon. Nickel's not that expensive. We don't need to beef up anything as far as volume goes. It's fairly cheap. So normally they don't throw carbon into that mix, but I'm writing it here just to keep it consistent. Out of these three, which one's the most used? Believe it or not, it's platinum. Platinum is the most used. It's really one of the most stable. We actually use platinum for a number of other reasons in a laboratory as far as equipment goes, believe it or not. So platinum is not that weird as far as these metals go. It's expensive, but it's not anything unheard of. Okay? This platinum/C, we often have a name that we like to use here. And sometimes this is going to be called the Adams catalyst. Just the name of a person that decided to use it one day. And all three of these give rise to hydrogenation. So the reason that I told you Adams catalyst is sometimes they'll write that into the problem. This alkene reacts with the Adams catalyst. Just to make sure you know what that means. I mean, that's why they do that. Other times they'll do what they've always done. Give me an alkene, and then they'll write H2, and they'll draw an arrow, and they'll write PT/C on it. And that's perfectly fine as well. But if you do read a question, and it does talk about the Adams catalyst, this is what they're referring to. I don't know if you'll see that or not in Blackboard, but this is what they're referring to if you do. All right. So the metal surface does not participate. It does not get involved in the product. It is only there to serve as a surface. And on the surface of these particles, that is where the alkene is basically going to be slammed against. And that is what makes this reaction go forward. Now, here we're just really talking about simple, little O hydrogen. And that's all that we're doing. Let me give you the overall scheme of this reaction to show you how complicated it is. So let's say that I have an alkene. Keep it simple. I'm going to add H2, and here I'm just going to write platinum. I'm not even going to bother writing the /C. I'm just going to assume that you know it's there, which is okay. And I ask you, what's formed? This is how I want you to answer the question. Here we have an alkene. And folks, this double bond, what do you think it does? I hope you go like I've been doing. Just make sure it doesn't sound like you're spitting up a loogie. And two sides of attachment open up. We're adding H2. H2 is H and H. What do you think goes on here? Hydrogen on one side, hydrogen on the other. Wow. Really difficult, isn't it? Again, nobody said organic was hard. Sometimes it seems like a lot. Sometimes it seems like a lot of information. Granted, I feel you. I've been there too. But this is all hydrogenation is. So what this means is that vegetable oil has a number of different double bonds, and we are partially hydrogenating them, which means that we look at these double bond areas in vegetable oil, and we break some of them using hydrogen gas. And we don't break all of them. We just break partial ones. Okay? Only some of them. And this will turn the oil into a semi-solid that you can cut with a butter knife. That's all that we do. So we take an alkene in this case, and we end up with an alkane. Folks, alkanes we talked about module 3, right? All of this stuff once again is coming back because at this point I should know how to name the alkene here. I also should know how to name the alkane that we get in the end result. That's all that hydrogenation is supposed to be about. That is it. No more than this. So I mentioned the mechanism. I told you this was a pretty simple overall reaction, and we just saw that. The double bond breaks. Hydrogen goes on one side, hydrogen goes on the other. The problem is that this mechanism is not really fully understood. Can you believe that? Can you believe it? We can understand the mechanism of something like alkoxymercuration reduction or whatever it was, but here we can't really understand the mechanism of just simple little low hydrogen. No, not really. You know, again, we know some of the details, just not all of them. There's no concrete proof yet. We're getting closer. But this is the way that they will present the mechanism to you in a textbook. And what you're seeing are these bluish, greenish orbs that are showing up on your screen. This is the metal catalyst, of course, that supplies the surface, and that surface is loaded with some hydrogen. So what you see stuck onto that surface, H2 here, H2 there, H2 here. This molecule with the purple lobes, of course, this is the sigma bond. That's the single bond that's initiated. And then the overlap of the p orbital. That overlap is going to be my double bond. It takes both of those orbs to create that double bond. Remember, you can't have just one or the other. You got to have both. So the overlap of that 1p represents the double bond. So that alkene comes into the vicinity of that metal catalyst, and the alkene will get near the hydrogen. And what you see here is that this hydrogen was stuck together, right? But here they've broken it apart. So hydrogen molecules settle on the surface of the catalyst. They interact with the metals. The alkene comes into the picture like a landing ship, and it approaches the surface of that metal catalyst, and then the hydrogens just kind of jump up and latch onto it. I mean, I think of like a Tom Cruise movie. He always does those crazy, stupid stunts where, you know, he's running and jumping onto a rope of a helicopter and they're flying off with him through a valley. Well, you know, these are Tom Cruise hydrogens. So hydrogens will jump up, grab a hold of the double bond, hold on to it for dear life, and that breaks the double bond and turns it to a single. We're left over with some hydrogens that are still on the surface of that metal. Those hydrogens have not been reacted with yet, but there's more alkenes that are in the vicinity. Those other alkenes will come in. Those other alkenes will eventually start taking up those hydrogens as well. So they're going to be used, just not immediately with that one particular alkene. So this is all that they're going to give you with the mechanism. No curvy arrows, nothing else. This is it. No more than this. And I'm okay with that. Again, curvy arrow mechanisms are great and all. And I like for you to know some of them, especially in the very beginnings of these reactions. But some of them are just downright useless. You know, you probably will never see them again. And quite honestly, depending on where you go from here and where you go from the second organic part, if you have to take it, you probably will never see them again anyway. So we'll talk about a few mechanisms. We'll get through them. We'll talk about curvy arrows. But we've got to be okay with the idea that we don't have a mechanism for every single thing yet. Okay. Here we actually see a comparison between trans and cis. So what this diagram is basically showing you is the reaction of hydrogen with platinum, and it's breaking the double bond down to a single to give us butane. And here we're doing the same thing. We're breaking the double bond with hydrogen and palladium, and that's palladium too. I think I said platinum, but that's palladium. And then we still get butane here as well. So we're getting the same products here in the very end. However, when we do this, we measure the amount of energy that we have to put into the system and what we get out of the system. And if you take a look at this, what we call heat of hydrogenation, there is a difference, all right? There is a difference between these two. So the trans molecule we said was more stable. That gives us 27.6 as far as the heat of hydrogenation goes. And those are going to be measured in kilocalories per mole, right? And then down here with the cis, we said these are typically a little bit more unstable as far as configuration about the double bond. Look at that. Module 3 information, Module 4 information, right? So this cis double bond is going to come through and it's going to break and we get butane just like we did before. But this time the heat of hydrogenation is 28.6. So this gives us an idea that out of these two, cis are more prone to be broken than trans. And one of the reasons is that trans is a little bit more stable. They're still going to undergo the reactions. It's still going to happen no matter what. It's still going to happen. But out of these two, there is a very slight difference between the energies that's associated with these products. And one reacts a little bit quicker than the other one. And we can see that using this diagram, using the heat this change of H, and using the double bond characteristics that we are comparing here in the very beginning. Okay? Now, this is going to lead me into a discussion on what we call stability of alkenes, because that's just really what we talked about here, right? We've talked about the difference between trans and cis, and I've just mentioned one is a little bit more stable than the other one. Trans is going to be more preferred over cis whenever they can happen most of the time. But folks, stability of alkenes can also be applied to things other than cis or trans. And what you're seeing here on the screen is a comparison between one of the least stable versions of the molecule to one of the most stable versions of the molecule. What I want you to do is focus on the double bond area. If you focus on the double bond, you're going to see this carbon involved in the double bond and this carbon involved in the double bond. Over here to the left-hand side, the only group that we have here is an isopropyl group, and the rest of these are hydrogens, right? This would be a hydrogen, this would be a hydrogen, that would be a hydrogen as well. We get one alkyl group, that is it. We've also kind of talked about this before in the past. In the middle, this is a little bit more stable, and this increase in stability is going to be due to the number of substituents that are on those carbons in the double bond. So here we have a carbon and a carbon involved in the double bond. To the left, we have a hydrogen and a hydrogen, but to the right-hand side here, we have a methyl group, which is one alkyl group, and we have an ethyl group as well, a second alkyl group. This gives that alkene a little bit more stability because of that. So we see a change of H that's a little bit lower. And then finally here, we see two carbons involved in the double bond. The one to the left has an alkyl group and an alkyl group. The one to the right has an alkyl group and a hydrogen. So we get three groups onto that double bond area, and that's a little bit more stable. So we see a change of H that goes a little bit lower because of that. So we can talk about stability of alkenes, right? We've talked about cis, we've talked about trans, but here we're looking at the number of substituents, the number of groups on those double bonds. That's what we're after. So if I wanted to sum this up, more alkyl substituents, the greater the stability. So down at the bottom, you're going to see a ranking. If the double bond has only one group, it's the least stable out of the bunch. Okay? Then if that molecule gets two, it becomes a little bit more stable. If the molecule adds on another, it becomes more stable. And finally, if the molecule has alkyl groups on all four sides, four legs of that carbon-carbon double bond area, those sp2 carbons, then this is the most stable out of the bunch. So if you do get these types of questions, that's how they're going to be read. They're going to give you some choices, and they might say, rank these in order of stability. And this is how you do it. You look at the groups that are on these carbons. The more groups that are on those carbons, the more stable that alkene is going to be. As far as cis and trans go, here's another diagram that kind of shows you this. We've probably seen it already. But on the cis version of that particular, to the left-hand side structure, you're seeing that these begin to overlap, and they have what we call steric strain. So the neighbors begin to bulge into each other's yard. They don't really like that. Okay, this privacy fence, it ain't good enough. It's still overflow. So because of that, they're a little tight. There's no wiggle room. There's no elbow room. Okay, we want to be a little bit further apart from each other. Those carbons also want that as well. So cis, for that reason, due to that steric strain, is a little bit unstable compared to the trans. And the trans allows these groups to be a little further apart. Notice they don't overlap anymore. Notice they're not invading each other's private spaces anymore, or personal space. Would you like that to happen? Well, these carbons don't like that to happen either. Okay, so here's more stability that we can bring in to the discussion. Cis is going to be less stable than trans. And then in our previous slide, what we saw was the order of stability according to the number of alkenes on that double bond. All right. So we've got about one more video left. And that one more video is going to sum up everything reaction-wise that we have learned up until this point. So stay tuned. You only have one left. But this one could be a doozy because we're getting to wrap up all of these tangents maybe into one video. However, the good news, the silver lining, is that you might watch this video and be like, oh, I get it now. Yeah, all of these separate ideas that were introduced is all coming back together. And that's what we'll do next. Stay tuned.